Okay, so hello everyone. I'm happy to share here our view on fuzzing. I tried to do a little bit like a summary what happened in the last year, and I tried to balance it like to be very neutral, but show some of our alpha how we do it. So first of all, like why we are here, why is fuzzing a problem? Of course, when we are fuzzing smart contracts, the main issue is, at least from our point of view, the number of integrations, which makes the state space very huge. If the state space was smaller, it would be easy to just fuzz it by brute force. Or if any one of you had a quantum computer, we would not need to be solving all these fuzzing techniques. But we are not there yet, so the statement is just that the state space is very big, and the question actually is like how to find the bugs in the state space. And I completely agree with the previous talk that the coverage, the percent of the coverage is not the thing that helps to find the bugs. That's not the metric. So we just need to focus on the techniques that help us to find the bugs where they are, and not to be fuzzing that state space that basically gives no value for the fuzzer. And the first, let's say, set of tools, I call that like machine-driven fuzzing. In this category fits the black box, gray box. It's basically something that you set up and let it run, and the machine does everything. So of course, into this category fits like Echidna, Medusa, and this kind of stack, where they are based on the two main techniques, which is coverage-guided feedback loop, and then some heuristics that is trying to cut also some part of the state space. So I guess you're familiar with the concept, but basically like coverage-guided feedback loop works on the principle that you put some random transaction, you see then where it got in the state space, and then you are favoring the path that explored the new code paths, and you are iterating over that over and over. The heuristics, it's something that basically is trying to give some more information for the fuzzer, so it can make better decisions, which can be, for example, coming from the static analysis, such as Slitter, and it can give some concrete addresses, or it can give some very edge values that also help the fuzzer to explore the states that are probably containing the bugs. So the advantage of this approach is that you set it up, you let it run. It's very effective in finding some bugs that the auditor would not think about. But the disadvantage why basically like we were not going by this approach is that sometimes the auditors, they have some idea. They have idea where the bug could be. And what we wanted to achieve is to be able to test this idea by the fuzzer easily, not wait if the heuristics or the state space exploration drive the fuzzer the direction that we want it to be. So that's the reason, so exactly like this limitation of this, how we call it, machine approach, is that the real bug can be hidden in some kind of like chain of events, for example, like 10 events that have to follow each other, and it's very hard for the heuristics to get there. That's why we tried to do it a little bit differently. And the second part is like human guided fuzzing, which we create a methodology, we call it manually guided fuzzing, and it kind of like explains what it is. So basically, we want it to give the power of guiding the fuzzer back to the hands of the auditor and not rely on heuristics or coverage guided fuzzing. And basically how it works, some of the principles are the same, so they are invariants. But what we introduce kind of like the new thing is called flow. And you can understand the flow basically like an integration test, which is defined by the auditor and is telling the execution path where the fuzzer should go, which is exactly can be the complicated 10 steps that have to be done in the protocol in order to test the happy path scenario. So this is the key part of the methodology. And then we have, because we like Python, so we always like implement in Python like a model of the protocol. It can be just a part of the protocol, for example, accounts. And then what we do is that we compare outputs from the fuzzer and outputs from the contracts from the outputs of the Python state, and of course it should be even. How does it look? Here's a very simple code snippet of some simple bridge. So basically, we can see here that we create a Python state as the first 2 lines. This is the local state that we are tracking, so the model can be as simple as this. And then continues the function, flow, deposit, and bridge. And this is basically the core of the flow. There is a flow decorator, which basically tells this is the function that we will be randomizing, for example, 1,000 times. And in this function, we have some built-in, for example, features like random account. So we select the random accounts, we select the randomness. Then we execute the transaction. And the first check is that we just have the stateless check to see if the event was emitted successfully. So this is nothing sophisticated. It just shows that the implementation is correct. But the fun part begins when we here manually update the Python state. So basically here we updated how we think the protocol should behave. And then we define the invariant. And invariant is executed after each flow. And in the invariant, basically, here we just compare that the state of our implementation equals to the state that's returned from the contract. So this is kind of like the easiest example of the manually guided fuzzing as we have it implemented in Wake framework. And by this, basically, we are giving the power to the auditor, which means the auditor has to have the idea how to create this kind of like happy path scenario or how to create some attack vector scenario. And the fuzzer just helps to test it on all accounts with all possible inputs and this kind of randomization stuff. Which means in the huge state space, we are not trying to cover the whole state space, but we are just like very selectively selecting the paths where we think the bugs are. And of course, the advantage is that we are leveraging the domain knowledge from the auditors. So basically, the auditor has the idea that the fuzzer helps to execute. But also, we observed one quite interesting thing, and it's that during the implementation of the fuzz test, because we have to implement the model, sometimes the auditors find the bugs that the fuzzer, for example, would not discover, but by forcing the auditors to think about the protocol and implement some of the logic of the protocol in Python, basically it opens the mind map in the head of the auditor, and this process helps to find the bugs. So also, like one part is the bugs from the fuzzer, but one important part is the bugs that help to, the fuzzing process helps to discover. I have some numbers here. So basically, most of the issues that are discovered by the auditors when they are writing the fuzz tests are the logical errors. So we have here the issues that we discovered in the last, I think, year. It's only highs and criticals. So almost half of that are the logical issues. So this is the stuff that is explored when writing the tests. And then we have here like data validation, denial of service, and this is the typical stuff that is discovered by the fuzzer. So even the process that we have is like helping to discover the bugs. But there is a problem, of course. This is very time demanding because actually like we are a little bit like rewriting the protocol in Python. So of course, there's a lot of manual work for that, a lot of boilerplate code. And also, when anything changes in the contract, we have to rewrite the model, which is something that the clients or the protocols who are paying for our time don't really like. So we are thinking like how we can maybe a little bit reduce the overhead, reduce the costs. And that brings us to the third category. And it's like, again, taking control a little bit back from humans to machine. And we try to do some AI-assisted fuzzing, which we, of course, named wipe fuzzing. And here we are trying to combine basically the two words together because the manually guided fuzzing works really well, but there's a lot of mechanical work. So the question is like if we can kind of change it to focus only on the security logic and not on the boilerplate code. So we tried, and the good thing is that Wake framework has a documentation, and we also have some playbook there with a lot of examples. So basically, when you open Cursor and just put it to the context, set up local environment and just tell the Cursor that check out the documentation, look at examples, it pretty much learns the framework. And then we are basically able to generate the boilerplate code by LLM. So all the loops, event handling, and stuff like that is generated. But of course, it's hallucinating. So the important stuff needs to be checked by the auditors, which in this case is mainly like the asserts, so what we are asserting, because sometimes the LLMs tend to be checking things that don't make any sense. And also we need to check that the implementation of the updates of the Python model are correct. And also the auditor is usually the guy who has the idea about the execution branch or the happy path scenario or attack vector scenario. And this is the stuff that the LLMs pretty suck at. They are not able to think as an attacker. So example here, basically the vibe fuzzing flow is that the prompt is something like create flow that mints tokens to a random recipient, check that only the owner can mint, verify token minted event, update token state balances. And it pretty correctly generates this boilerplate code. So here is the flow function. There is the initialization of the random parameters. It does the transaction. But then here, where is the actual event handling and where is the updates of the local Python model, here it kind of makes mistakes. So this is the part that still the auditors need to write themselves. But we have kind of solved part of the problem that at least half of the code now can be vibe coded because the LLMs understand the framework. And by this approach, we of course reduce the main pain point, which is the development speed. So now we are much more efficient in writing the model. We are able to solve by this kind of the updates of the protocols because the LLM can do it. And there is still pretty good safety net, which means when there is any hallucination or anything, usually it means it fails, which means it produces false positive finding, which we can then debug and see that, okay, the logic implemented by the LLM was wrong. And the question is if LLMs can do it all. So not yet, but this would be, of course, kind of North Star to have vibe fuzzing framework that would be fully autonomous. So back to the machines. We see there are three main limitations. So the workflow would be easy, just the AI generates the test in Wake framework, executes that, and auditor just reviews the results. But the main problem, number one, is that what we do during the manually guided fuzzing is basically we read the documentation and rewrite the key mathematical formulas in Python, which basically means we are rewriting the protocol. So for the LLM, it would need basically to wipe code the whole protocol from documentation, which usually is in Web3 sucks the documentation. So that's the main problem, that the LLMs basically cannot reproduce the protocol based on the data that they were given because the data are not prompts for LLMs. Second problem is when I touched a little bit that when the test fails, still there needs to be someone who checks if either the test is written incorrect or if it's a bug. So this still kind of this triage needs to be done by humans. And third problem, still human creativity is the best in finding the security narratives, which means usually LLMs are trained on the data that were there, but the attack vectors are evolving, are new. So this is the key input that still, at least for now, needs to be done by humans. But if we solve these three questions, we can have fully automated AI fuzzing. So yeah, that was my talk. It was quite quick, I see. So if there are any questions, feel free to ask me.
On one of your slides just now, you said there's a potential for so if AI makes the model, then usually those bad tests are filtered out as false positives. Well, what about when they're not? It makes two mistakes that cancel each other out or something. Or like you said with the balances, it reproduces the over-underflow. issue?
Like the main problem is that the AI doesn't create a model, because for that we don't have the data such as the documentation and stuff like that. Or if it creates the model, it creates the model from the solid code, which is wrong, because basically the idea here is that we are not affected by the solid code, so we don't re-implement the possible bugs in Python. So basically we have to look at it like implement the model without looking at the solid code, which LLMs cannot do right now. So basically this is the main problem in setting this workflow.
I mean, like a human can also make the same mistake, right? Which
Yeah,
is
yeah,
like reproduce the bug.
but human can do such things. I don't know. Ask on a Slack channel, hey guys, how does this work? You know, I'm trying to figure out, and this is the thing that we don't have in the AI workflow. Okay, so thank you very much, and see you soon.